A more convenient way to derive the deflection and slope is through a method that we call conjugate beam method. Basic principles of relationship between the load, shear, and also moment. We already know that the derivative of your shear with respect to x, which is the location along the beam length, will give you the load. Okay, just let me write it down here. dv over dx will give you the load. Okay, and similarly, if you do the same, the derivative of your moment with respect to x will give you your shear. Okay, so load, shear, and also moment, they are related to each other. That's why you can easily draw the shear force and bending moment diagram, and once you know the slope and also the area under the graph, basically. Okay, so if you want to relate your moment to your load, okay, dv over dx is your load, okay, and you know that your shear is the derivative of moment with respect to x. So if I were to write this down, okay, v is dm over dx, okay, this it will be equal to my load. Okay, so basically, if I rewrite this, I will get d squared m over dx squared is equals to w, or your load, and this is what I get. Sorry, this is basically what I get from the first equation. Right, and this is basically the relation between my load, shear, and also moment. And also from the beam theory that we have done before this, which is related to your double integration method, we also know that d theta over dx. So basically, we know that d squared y over dx squared is m over ei. Okay, if I rewrite it down, I will get d over dx as dy over dx. Okay, I rewrite this. I will still get m over ei. I just take out the internal punya dy dx ni. Okay, it's the same thing. Okay, and I know that dy over dx is basically my theta. So okay, d theta over dx will give me m over ei. So this is where it basically comes from. Okay, so d theta over dx is m over ei, and d squared y over dx squared is also m over ei. So if you look at these two equations, okay, the first line is coming from load shear moment relation, and the second line is coming from slope deflection and also moment relation. You will see that the relationship looks very similar in the sense that W in your load moment relationship is m over ei in your slope deflection moment relationship. Okay, and your V here is basically theta in this equation. Okay, similarly here, W is still m over ei, but your m now has become your y. Okay, so it looks similar. It's not the same exactly. It is not the same at all. Okay, but they have the same relation or the same shape. Right. Continuing, if you integrate your shear, you will get. If you integrate your load here, you will get your shear. This is coming from this first equation. So basically what I did was, this is my relationship for my shear. So if I integrate it, dv over dx with respect to x, I will get w. Okay, I have to integrate both left and right. So I'm going to get v is equals to integration of w with respect to x. Okay. Okay, and if I do the same thing for my moment, okay, integrate it twice, dm over dx, okay, integrate it twice of w dx, and basically if I integrate it twice, I will get my moment. Okay, so my shear is the first integration of my load, and my moment is the second or double integration of my loading. Okay, so that's the relation. Okay. But basically, I mean, just to recall, kan, so moment is the single integration of your shear. So that's why area under the graph of your shear force diagram is basically your moment, okay, because it's the first integration of shear or double integration of the load. Okay, and I repeat the same thing for the second line of the equation, which relate my rotation to my moment. Okay, so rotation is a single integration of m over ei dx, and the deflection is the double integration of m over ei dx. And you see here again, it has similar equation, similar form of equation. It's just that rather than shear, at the second equation you got rotation, rather than load you have m over ei, and rather than moment you have deflection. So what we are going to do is we are going to tap into this similarity, and we are going to use conjugate beam method in order to solve for this problem by looking at these two similar relationships. So to solve using this conjugate beam method, okay, what we are going to do is imagine that you have a real beam here. Okay, this is your real beam, and for this real beam, you are going to you want to find this deflection and also your slope, displacement, and also slope of your real beam. Okay, so this is your real beam. So your objective is to find the slope and also the deflection. So what you are going to do in this method is you are going to create an imaginary beam, and this imaginary beam is what we call as our conjugate beam. Okay, it's the same beam. The only difference is the loading and the support. Later I will show you. But the main difference is the loading, where your loading, instead of W, you are going to change your load to M over EI. This is going to be your load. Okay, so if you change this load to M over EI, so this load you change it to M over EI, and this load you change to M over EI. So in the conjugate beam, if you cut your section and you find your shear and moment in your conjugate beam, so if you find your shear and moment inside your conjugate beam, okay, it will actually be equal to the slope and the displacement in your real beam. Okay, again, I repeat. Okay, say you have a beam having whatever load that it has, which is W. You change this load into M over EI. Okay, the moment divided by EI. So you change all this W into M over EI. Okay, so if you want to find, if you cut the section at any point and you want to find the shear and also the moment, okay, basically the shear and the moment that you get from your conjugate beam will be equal to the slope and also your rotation in your real beam. So this is what conjugate beam method does. It creates like an imaginary or another beam that is called conjugate beam. Okay, by putting different boundary, a little bit, by modifying the boundary condition and also your loading to M over EI, and then finding the internal moment and forces in order to get the deflection and also slope of your real structure. Right, whenever you want to find the slope on your real beam, okay, what you do is you find the shear on your conjugate beam. So if you find the shear in your conjugate beam, you basically will find the slope at your real beam. And then whenever you want to find the moment, the displacement on your real beam, okay, you basically have to find the moment on your conjugate beam. Okay, yeah, recall the previous slide on the relationship between the similarity between the moment and the displacement and the shear and the slope. Okay, so this is the theorem that we are going to use to solve for our. Okay, so what you need to do is you need to just know this. Okay, if you have an actual beam, the slope and the displacement, okay, would be your shear and also your moment inside your conjugate beam. But make sure that you change the load on your conjugate beam into this M over EI. Okay, put M over EI in and then you analyze. And I think this is very easy. I will show you in this example. Okay, one thing to note is that you also need to make sure that your support condition is similar between your real beam and your conjugate beam. Similar in nature, not similar in shape. Okay, for example, this one. Okay, if your real beam is pin, okay, so if this point is pin, you know that pin doesn't have any displacement, okay, because it's a pin, right? But it has rotation at this point. Theta, you will have a value of theta, but your displacement is going to be equal to 0. So recall that theta of your real beam is equals to your shear on your conjugate, okay, and displacement on your real beam is equals to your moment in your conjugate. Okay, so what you need to do is you need to make sure that your conjugate beam has the same relation as your real beam by changing the support if it's not. Okay, so if your real beam is pin, okay, you have to make sure that rotation, you will have a value for rotation, but your displacement is going to be 0. So basically, your shear at that point, you have to get a value of shear, but your moment has to be 0 inside your conjugate beam because that's how they are related. Okay, so by changing it still to pin, okay, by having a pin ended of your conjugate, okay, you will make sure that you have shear on this support, but your moment is going to be 0. Okay, so if you change your real beam from pin to a conjugate beam, which is also pin, you will satisfy the condition. Okay, they are both the same. Okay, similarly for roller, okay, it's going to be the same. Okay, but supports other than that, you need to modify it so that it will follow the rules. For example, okay, if you have a fixed end, okay, for fixed end, you know that you cannot have any slope, okay, and your displacement also have to be 0. Okay, but if you remain your conjugate as fixed, if you have the same boundary condition for fixed, you know that fixed, you will have shear. There will be shear and there will be moment. Okay, so these two relations are not the same. Okay, they are basically different. So what you need to do is you need to change your conjugate beam into a different boundary condition where you need to make it free. So at this point, if your real beam is fixed, your conjugate beam has to be free. Why does it has to be free? Is because you want to make sure your shear is equals to 0 and your moment is equals to 0 so that their relationship is similar. Continuing, okay, when you have a free end, so you know at the free end, your structure can move anywhere. So the deflection is not going to be 0. You will have a value of deflection. You will also have a value for slope, okay, for your real beam. So to make sure that your shear and also moment of your conjugate follows the same rule, you need to change your conjugate into fixed. Okay, so by changing your conjugate beam from free to fixed, okay, fixed you will have a value of shear and you also have a value of moment. Okay, so the two relation are similar. Okay, similarly, if you have an internal pin, you know that the slope is going to be not equal to 0. You can have different value for slope for internal pin. So if this is your pin and this is your beam, okay, so you can have slope. Okay, you can have values for slope. It's just that the deflection, it cannot go up and down, okay, at this point. So your deflection is going to be equal to 0. So to make sure that similar relation is in your conjugate beam, you need to change from internal pin to an internal hinge. So what's so special about a hinge? Your moment is going to be equal to 0, but you have a value for shear. So again, as shear is related to slope and this deflection is related to moment, then it satisfies both conditions. Okay. And then if you have internal roller, it's similar to internal pin. So these two are basically similar. And then if you have real internal hinge in your real beam, so internal hinge, you can have rotation. It can rotate, and it can also deflect. Okay, it can go down. It can also rotate. Okay, so in order to have this condition, you need to change from internal hinge to an internal roller in order to get that value. Okay, so these are basically what you need to do. Okay, these are just examples of how to change it. So if this is your real beam, simply supported, your conjugate beam will also have simply supported. Okay, so basically you need to change all of the supports on your real beam to a conjugate. So these are the two supports. So if it's a pin and roller, so for your conjugate, it will remain as pin and roller. Okay, if it's a fixed and free here, okay, you need to change the conjugate beam into, for fixed, you need to change it to free, and then for the free end, you need to change it to fixed. Okay, if you have this, what we call it as pin, okay, your conjugate beam will remain as pin, right? Here, this is an internal roller. You need to change it to internal hinge. And at the end here, this is free. You need to change it to fixed. Okay. Continuing, many examples. If it's free here, you need to change, fixed. You need to change it to free for your conjugate. Internal hinge, change it to internal roller. And roller will remain as roller in your conjugate. Okay. Finally, fixed becomes free. Internal roller becomes internal hinge. Okay, internal hinge will become internal roller and pin will remain as pin. Okay, so make sure that you change all of the boundary condition appropriately. Conjugate beam is loaded with M over EI diagram. So of the real beam. Okay, we'll see one example. Load is assumed to be distributed over the conjugate beam when M over EI, your moment is positive. Okay, you remember this, arrow is upward. This is the notation that we are going to use. When positive, arrow is upwards. When M over EI is negative, arrow is downwards. Okay, so arrow is always towards the beam. Okay, so usually the beam is like this, downward. Okay, if it's positive, go upwards. All right. This one you have to remember. Okay, let's. And in this example, you are asked to find the slope and deflection at point B. So basically, what I would suggest you to do is just write down what you need to find. Slope at B and deflection of B. Given E as 200 gigapascal, this is basically steel section. And you are given also I, moment of inertia. Okay, you have a beam with a load at the middle. Okay, so before we start, I would suggest you to draw the deflected shape. So this is cantilevered. So what's going to happen is that the whole thing is going to deflect downwards. Okay, between the loading, let's call it as point C. C and B, you don't have any load, so the beam will remain straight. This. Okay. There's a curve between A to C, but between C and B is straight. Okay, then what you're going to have is some label. So what is deflection at B? This is basically deflection at B. And what is slope at B is if you draw the tangent of this line, okay, and draw the original vertical or horizontal line, this angle is your slope at B. Okay, so you are asked to find these two values. So what you need to do is first, okay, the first step that you need to do is to draw the bending moment diagram of your real beam. M over EI diagram, sorry. So that's why if you are struggling with drawing bending moment diagram, then you are going to have difficulty in this exercise. Okay, so how do you draw M over EI diagram? So you basically have to calculate your reaction. Okay, you have 20 kilonewton going downwards. Distance is 5 meters to 5 meters. Okay, so this will be your shear, 20 kilonewton, and this will be your moment. Moment is basically 20 times 500. Kilo Newton meter. This is the unit. Okay, so after that, you basically use whatever method that you have learned in the frame analysis. So if you look here, okay, this is your tension is going to be above the line, okay, and your compression is bottom. Okay, so basically it means that your bending moment diagram is going to be above the line. Okay, so if you do this, okay, this is a negative moment, so it goes up and the value is 100. Okay, and then you don't have any load. Better yet, okay, sorry, sometimes I go ahead of myself. If you are good, you can draw bending moment diagram directly. If you are still struggling, I would suggest you to draw the shear force diagram first. Okay, so shear force diagram, it goes up by 20 and then constant, and then it goes down. Okay, so this is your shear force diagram, and your bending moment diagram. Okay, you have a point moment at this end here. Okay, it's 100, and this is a negative value. Okay, so go up by 100. This is negative 100. Okay, and then you calculate the area under the graph. It's 100, and then this shear is constant. So your moment, your moment is linear. Okay, and straight line go down. Okay, let me just draw it again. Okay, if you have noticed, I have kind of a bad handwriting. Okay, so this is your bending moment diagram. Okay, then what you need to do is you need to draw your M over EI diagram. So what is M over EI diagram? So M over EI diagram is basically whatever moment that you have, you divide it by EI. And it's useful if your EI changes lah. If your EI doesn't change, then it will remain as it is. So it's going to look something like this. Okay, this is negative 100 divided by EI at the highest point here. Okay, and this is 5 meters at the 5 meters. Okay. Recall that this is your real beam, and then this is your M over EI diagram. Okay, so the next step after you have drawn your M over EI is to draw the conjugate beam. Okay, so what's a conjugate beam? Okay, conjugate beam is a beam that have probably similar or different support reaction, okay, depending on dia punya relation. Okay, and the loading on your conjugate beam should be your M over EI diagram. Okay, so what you need to do is to construct your conjugate beam, and remember, the first thing that you need to make sure is that your conjugate, you remove the load that you have on your structure. So originally you have 20 kilonewton, and I see that this is like a common mistake that students do, even though I told them many times not to do it. Okay, first of all, remove the load. Okay, number one, remove load on rear beam. Okay, do not have the load. Okay, the second step is to change the support condition to follow whatever that I have shown you before. Okay, so in this case, if your support is fixed, then for your conjugate, it should be free. So this is fixed, your conjugate has to be free. Okay, look, and the end here on the right side, this is free. Okay, so for your conjugate, it should be fixed. Okay, so this is your support condition. Okay, do you have any intermediate support? No intermediate support, so should be okay. And the third step would be to apply the load. Apply M over EI as load in conjugate beam. Okay, so you see this load that you have here. Okay, this is the M over EI diagram. What you need to do is apply it as a load on your conjugate beam at the same point, same value, same location. Okay, so this is a straight line, hopefully. This is a straight line that goes here. So it's basically a triangular load with a value as negative 100 divided by EI. Okay, after that, make sure that the arrow is always pointing towards your beam. So the arrow is basically downwards like this, towards your beam. So negative m over ei, the arrow is downwards. Okay, so you can basically remove this negative sign. Okay, don't worry about the negative sign. Okay, we are going to follow. So what you are asked to do for this question, don't forget, so what you are asked is to find the slope at B and the vertical deflection at B. Okay, so the slope at B and deflection of B would be equal to, for the slope, it's going to be equal to your shear at B inside your conjugate beam, and the deflection at B will be equal to the moment at B for your conjugate beam. Okay, so in order to find these two values, what you need to do is you need to find the internal shear and moment at point B. This was for your conjugate. So for your conjugate, this is point A and this is point B. So what you need to do is find the shear at B and also moment at B. So following, it has to follow the same sign notation that we use. Okay, so in order to solve for shear at B and moment at B for your conjugate, okay, so you need to determine where. So say I want to find the slope and deflection at B. So what I need to do is I need to cut at B just to the left of the support, okay, and then equate the shear force and bending moment at point B. So this is how my load is. Okay, like this. This load is 100 over EI. Okay, this is 5 meters. 5 meters and 5 meters. And what I'm basically doing is I'm cutting just to the left of point B to find the internal forces. This is shear at B and this is my moment at B. So if I find these two, they are basically my slope and also slope and deflection at point B. Okay, so how do I do that? Very easy. Is this equilibrium? So you sum the force in y direction, you will get your VB. So let's assume positive as upwards. Okay, so you have a triangular load. So the triangular load, it's a negative value downwards. Okay, so it's a negative of half times 100 over EI times the length, which is 5 meters, half times height times the support. Okay, this will give you force. Okay, and then minus shear at B. Okay, equate it to 0. You will find shear at B equals to, let's double check, should be equals to negative 250 over EI. So this is shear at B, and if you want to find the moment, you just sum the moment about point B. Just assume one direction as positive. I'm going to assume clockwise as positive. Okay, so the force here, so it's this is clockwise, so it's positive. Half times 100 over EI times 5. Okay, this is my force. Okay, and the force has to be multiplied by a distance. So how much is the distance? Okay, the resultant or equivalent resultant force here is here, which is basically 2/3 of the length. Okay, so it's going to be 2/3 times 5. Okay, but this is just the length to the end of the this is basically just the length from the load to the end of this triangular, so you have to add with 5. So plus 5. Okay, and then plus, so these are the full force times the arm length distance. Okay, and then add it with MB. Okay, it's still positive because it's clockwise. Equate everything to 0. So if you do this, you will get MB equals to negative. Hopefully I got it right. 2083 over EI. Okay, this is what I get. These are the values that I obtained from the previous calculation. Okay, so the shear at point B in my conjugate beam is negative 250 over EI, and this would actually be my rotation at B for my real beam. Okay, and then for the moment of my conjugate beam, this is going to be equal to my deflection at point B of my real beam. Okay, so having said this, then if you want to find the slope at B, okay, it's just whatever the value is, okay, plug in the correct value of E and I. Okay, my suggestion is, since your 250, you are deriving it based on your unit load and distance as kilonewton and also meters, kan? You use kilonewton and meters. So for EI, make sure that the unit is in kilonewton and meters. E is stress over strain. So the unit is basically stress, kan? So it's change the unit to kilonewton per meter squared, and I change it to meter to the fourth. Okay, so that if you ensure that their unit is consistent, you don't have to worry about the whether or not your answer is correct. Okay, so if you do this, you will get a value of negative 0.00263. Okay, and the unit would be in radians. Okay, it's not degree, radian, it's radians. What is negative rotation mean? It means that the rotation is clockwise. Clockwise is a negative rotation. Okay, similarly for displacement, so the displacement at B is equals to negative 2083 divided by EI. And make sure the units are consistent. For E, you use kilonewton meter. I, you use meter. Okay, if you use a consistent unit, you are going to get a value of negative 0.123, probably 0.0219 meters. Okay, or you can rewrite it down to negative 123, negative 21.9 mm. Okay, you can do this also. Okay, so what is basically mean, if it's the value is negative, it means that the deflection is downwards. So please make sure that you have two things. Okay, values are obviously, but have the unit, whatever it is, whether it's radians, meter, or mm, and then the direction, whether it's clockwise or counterclockwise. For rotation and for deflection, make sure that you have the correct direction. So what you need to do is, I guess you need to check back and make sure whether your answer makes sense or not. So this was your beam. Let me just redraw my beam. Okay, and I have a load at the middle. So what's happening is that the beam is deflected downwards like this. Okay, so just make sure that everything is okay. This is my deflection at B, and it is going downwards, so correct. Okay, the second one is the slope. So basically you draw the tangent of the line and the original horizontal position, and then check whether the rotation from the original, whether it's clockwise or counterclockwise. So in this case, origin is here. Originally it's horizontal. The new one is in, let me use purple. The new tangent is purple. Okay, so the arrow is pointing towards the new direction. So it's clockwise. So it's negative value. So that's how you tell. So always double check with your assumed deflected shape. Make sure that this makes sense. So this is the whole thing about conjugate beam. So it's pretty easy, but it can also get more complicated if your M over EI diagram for your real beam is say parabolic, and that will be different, a little bit difficult. Okay, fully in this last example, okay, you are asked to find the maximum deflection of the steel beam shown in the figure. So maximum deflection, okay, if your structure is symmetry, okay, usually the maximum deflection is at the middle and at the known point lah, whether it's at the sides or at the middle. Okay, but if like this, your structure is not symmetry, your load is 9 meters away from point A and then point B is 3 meters away. So this is not a symmetrical structure. So you don't know where the maximum deflection is. Okay, so how do you determine the location of maximum deflection? Okay, again, as I mentioned before, this maximum deflection is a function, is usually our equations are a function of curve kan. So if you want the maximum of something, if you have a curve and you want the maximum of something, is basically the slope. The slope of that line has to be equals to 0. So then you get the maximum. Okay. So what is slope? Slope is dy over dx kan. So you just check where the point slope equals to 0. Okay, along your beam length, and this is where the deflection will be maximum. Okay. So they are basically just equations that relates. First of all, look at the left side. Don't look on the right side first. Okay, look on the left side. Okay, so for the left side, this is your real beam. Okay, you have a load here. This is point A and this is point B. So if you look at the deflected shape, which is here, this is how your beam will deflect at the support A, which is your pin. Okay, it doesn't move, and at point B also it doesn't move because it's a roller. And the maximum deflection should be somewhere in between, which we don't know the location yet. Okay, so if you want to solve for conjugate beam method, what you need to do first is you need to draw the moment diagram. Okay, so if you are not familiar with bending moment diagram, you don't skip the shear if you're not familiar. Find the support reaction, okay, and then draw the shear force diagram, 2, and then 6, and then like this. This will be your shear force diagram, and then your bending moment diagram will basically be straight lines. Okay, and the value is 2 times 9, which is 18. Okay, again, if you're not familiar, don't directly draw your bending moment diagram, draw your shear force diagram first. Okay, next step, draw M over EI. So divide this thing by EI, okay, and divide. So this value will be divided by EI. Okay, so once you have this, the next step is to draw your conjugate beam. So how do you draw the conjugate beam? Okay, at the beginning, okay, have a beam and then check the support condition. So at A is a pin, at the conjugate beam, pin remain as pin. Okay, and then at point B at the other end, this is a roller. So if it's a roller in your beam, your conjugate also remain as a roller. Okay, and then don't forget, do not put this point load on your real beam. Do not put it. Okay, and then what you need to do is you place your M over EI diagram, okay, inside your conjugate beam. So this is your M over EI diagram. Okay, exaggerated. Sorry, darling. Let me just rub it off. Okay, so this is your M over EI diagram. Okay, how about the arrow? Because your load always have arrow. Arrow should always be pointing towards your beam. So if it's a positive moment, it goes upwards. If it's negative moment, it goes downwards. Like this. And the value here would be 18 divided by EI. It's basically your M over EI diagram. Okay, once you get this, then you can basically solve for your problem. Continuing, I know that my maximum deflection would be somewhere in between the load to your maximum applied load. Like this, So I just rewrite it. If you forgot how it looks like, this is your simply supported beam, and you have a load. So usually, if you have a load that is skewered on the right side or on the left side, the maximum deflection is usually somewhere here. Okay, it's on the left of your support, if your support is towards the right side. Okay, if your support is towards the left side, more towards the left side, usually the deflection is on the right side, the maximum deflection. But if you're not sure, okay, you need to cut your beam at two sections, basically. Okay, so if you are assuming that this is A and this is B, and this is, sorry, wrong. Okay, so this is your A, this is your B, and the point of loading is called C. Okay, so if you are sure that your maximum is between A to C, what you need to do is you need to cut in between A and C. This is C. Cut somewhere in between. Okay, get the shear and also get the equation of moment for conjugate beam with respect to X. Okay, so what the first thing that you need to do is you need to find the support reaction first. Okay, here and here. How do I find the support reaction? Because at the beginning you don't know the support. You only know that this is pin and roller, and then you have a load like this. And okay, first of all, you need to find your support reaction. So reaction at A, what you do is you sum the moment about point B. Okay, sum the moment about point B, you will get RA. Blah 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 blah. Okay, this is how much I get. Please try on your own using equilibrium. And then you can find reaction at B by summing the force in Y direction. You will get your reaction at B. Okay. So once you do this, you cut somewhere between A and C. So this is how I do it. I cut it somewhere between A and C at the distance X. Okay. And I tried to find the equation for shear and also equation of moment. So when you are cutting something, the height is 18 divided by EI kan? Okay, this is the height here. So if you cut at any point of X distance, so the length here will just be a ratio. So this 9 meters has the triangular height of 18. So if you just cut it at X distance, this will be just the ratio. So 18 over EI divided by the total length, which is 9 meters from A to 18 EI, this is 9 meters. Okay, and then multiply by the length that you are talking about, which is X. Okay, so the height here you will get as 2EI X. 2X divided by, sorry, repeat. You will get 2X divided by EI. So that's how much the length here. They are basically the ratio of triangle. Here. So if you have a big triangle, okay, and you want to find the height of this, whatever distance your triangle have, okay, so you just take the ratio of the angles. So very easy lah. So you get 2x over EI. Okay, so this, you don't know the distance kan, because you are cutting it at an arbitrary location at X here. So that's why there's a function of X here. Okay, internal force, when you cut it, you have shear and you have moment. Okay, so if you want to find what's the value of shear, okay, you just sum the force in Y direction. Okay, you will get your shear. Okay, your shear is going to be equal to this equation. Okay, they are basically the rotation of your real beam. And then if you sum the moment about point X, you will get this. Okay. Sorry. Reverse. Sorry, wrong. This is just the same equation. So simplifying this equation, okay, because you want to find displacement maximum will occur at slope equals to 0. Okay, so what you need to do is you equate your slope as 0 here. Okay, and basically you need to find what's your X. So X is equals to plus minus 6.71. Since 6.71 is between A and C. Okay, A and C is 9 meters. So since it is in between A and C, so this value should be positive 6.71. Okay, and then what you can do is find the moment at x equals to 6.71. Okay, so you just sum the moment about that point. Same free body diagram. Okay, so now you sum the moment about point x. Okay, so you get mx, this one, okay, plus the support here multiplied by x, so 45 over ei times x. And then you have loading here, but it's opposite direction, clockwise, so minus. Okay, the triangular load, this one, multiplied by the moment arm. You equate everything to 0, and then you will get mx equals to this equation. Okay, and then because you know already where the location of x is, 6.71, if you plug it in, okay, you will get a value of moment as negative 201.2, okay, which is equal to the deflection of your rear beam. Okay, so your deflection of your beam is negative 16.8 millimeters, and because it's negative, it's basically downwards. Okay, say from previous calculation, okay, if you recall, and you got x equals to, so basically what you do is your shear of your conjugate is equals to the slope of your real, and then you equate it to 0, and then you get your x. Okay, say your x is not in between the range that you are expecting. So A to C, the equation that you develop here is when x is between 0 to 9 meters, okay, A to C. So say when you do this, okay, you don't get in this range, it simply means that most probably the deflection is not between A to C, the deflection is between C and B. So you need to also cut that at that point and then check the maximum value. Okay. Right, I have additional exercises 5, 6, and 7 if I'm not mistaken. Okay, I will give you the answer, but I hope you try it first. So if you have change in moment of inertia, you have I that is a little bit different. What you need to do is you need to draw your moment diagram first. Okay, you draw your moment diagram, and then divide M with E and I, which I changes now to whatever value that you have. Okay, make sure that you change the M over EI diagram. Okay, so that's about it for conjugate beam method. Hopefully you understand the step-by-step procedure. The difficulty of the question is, again, I can only show you 1 or 2 examples, and the rest you have to try it on your own. Okay, thank you very much. See you next week. Next week classes will be face-to-face as usual. Thank you.